Hey Joe, I'm just going to first show you a little few pages from the textbook. So on page 3 in the book, you saw the situation where when you had two equations represented with two variables, if they had one solution, it represented the intersection of two lines. And if they were parallel, that's no solution or an inconsistent system. And then here you have the same equation essentially, so you have an infinite number of solutions. Okay, next I'm going to take you to page 6 to summarize. If you have three equations and three variables, this example showed you how if you had one solution, 1, 0, negative 1, that's three planes and they intersect at a point. Okay, now you could have three planes that don't intersect along a point. So in fact, here are some scenarios: three planes that are parallel, or three planes that intersect along a line. Think of it like the binding, and this is a book with all the pages. Okay, and that's like the binding there. And this is the three planes that meet at one point. If you look in a room, think of the walls, two walls as a plane and the ceiling on top, and they meet in the corner. Okay, that's the point. You could also have three planes such that not all three intersect at the same time. Two of them could intersect, but not all three. And same way here, not all three intersect simultaneously. So there's a lot of little stuff going on. Okay, back to the book. I wanted to go to page 8 next. And in page 8, I want to show you this picture where two of the planes were intersecting and the system was inconsistent because the third plane did not simultaneously meet the second and the first planes there. Okay, so and then page 12, I wanted to show you something there. So this is a scenario where the point 3, 4, negative 2 satisfies this plane and this pink plane, but it's not in the blue plane. Okay? Now, on to your question. I want to first give you a visual on, I have a plotter that I use in Calc 3 when I teach it. It's called CalcPlot 3D. So to use it, I'm going to type in the equations you did in the practice problem. So I'm going to enter, your first plane was x1 plus 4x2. I'm going to use x plus 4y instead, minus 5z equals 0. And that'll give us our first plane. And then I'm going to do that again. I'm going to select implicit surface and type in your second equation was 2x1 minus x2 plus 8x3 equals 9. So I'll use x, y, and z instead. There's our second plane. Your solution in parametric form. So I'm going to take a quick detour after this graphing and do a little parametric review for you. So parametric surface, I think I want space curve. So your solution, I could write it, you know, your free variable that you got, x3, I'm going to call it t, that's your parameter, 4 minus 3t, and then you had negative 1 plus 2t, and just a t. Okay, graph that. And you'll see that that is the blue line that showed up as your line of intersection. Okay, so that's the geometric perspective. Okay, and I'm going to take a little, go in my document camera next. So in Calc 2, which you probably took a while ago, you saw on your graphing calculator a parametric mode, PAR, right there. So I'm going to go to that. Let's say you have an equation like y equals 2x minus 3. Parametric form for that would be you could let x be t, then y would be 2t minus 3. So I'm going to input that in there. X is t, and this is 2t minus 3. Okay, and you get the graph of a line. Notice the graph doesn't go on forever because of our t min and t max. So I could increase that and make it like negative 10 to 10. Then that line will actually go longer. Okay, so that's your metric form in 2 dimensions. Okay, in Calc 3, I'm not sure if you took Calc 3, but in Calc 3 you learn that a line in space, a line in R3, has this form. X equals x naught plus at, y is y naught plus bt, and z is z naught plus c times t. Okay, now Calc 3 is not a prereq for this course, but I do a quick explanation in linear algebra. This part here is an extension from Calc 2 of what you saw in 2D. Okay, you just have a z component. So x naught, y naught, and z naught are fixed points on the line. Some point on the line, and then a, b, and c are the direction vector. So it's like the slope in 2 dimensions. So this was slope, right? Mx plus b. So it's kind of like the slope. And t is your parameter. It's any real number. So this is the parametric form of a line. So any real scalar. So the solution that you got in the practice problem was of this form because the two planes intersected along a line. Okay, let me just switch back to the book for that. All right, so this was the solution to that first problem. And here you solved for x1 and x2, the basic variables, and x3 was your free variable. And that free variable ends up becoming the parametric part, the parameter rather, so we call that to be t. Okay, so this was x1, okay, equals 4 plus t times negative 3. Okay, and that's what I entered into that 3D plotter. Okay, so if you can look at, I'm going to copy that down from the book on my document camera, and then I'll switch and show you what I did. So I'm going to copy this portion. So you have 4, negative 1, 0, plus x3 times negative 3, 2, 1. All right, let's switch. So this is what I just copied down. And if you think of this x3 as parameter t, then this is x equals 4 plus t times that, so it's minus 3t. Then y, the second variable is y, it's negative 1 plus 2t, and then z is 0, so 0 plus 1 times t. Okay, and you can't really plot that on the TI calculator because it's an R3, and that's why I took you to that Calc Plot 3D that I really like. I use this in Calc 3 in my classes, so you can do a lot of cool things in there. So if you're interested in learning more about that, we can certainly meet face-to-face. So hopefully this helps a little bit and answers your question. If not, please feel free to let me know.